So we look here. It looks like I've got a lot of new people on here. So welcome. I'm Mr. Jackson. I'm your chemistry teacher. Hopefully, you're in the right place. Let's see who we got today. Take it a little bit easy today. Welcome back. Hopefully, you guys are doing okay. Let's see if I can get a list. A list of names. All right, let's see. Cassidy. Welcome, Cassidy. I don't think I let you last semester, right?
Yeah, you did.
I did?
No.
No. Well, welcome. Ann Vaughn. Welcome. Brianna's back. Hopefully you had a good break. Brianna? Maddie. Maddie, welcome back. Who is Ka? Ka3. Okay. Welcome.
Yeah, I'm here.
Excellent. I just didn't have you last semester. I wanted to welcome you. Sydney, we had you last semester, right?
Yeah, you had last semester.
Welcome back. Landon Warner, welcome. Michaela Rami or Ramey?
Ramey, hi.
Hi, welcome, Michaela. Michaela Ramey. Are you related to Mrs. Ramey?
No.
No. Okay. Yeah. I mean, obviously not. Maybe Mrs. Ramey, but not the right Mrs. Ramey. The one that teaches at school now. Amani, welcome back. Good to see Amani here. Are you coming back on the 19th or whatever, Amani?
It really depends on what my parents think due to cases rising and stuff. So I don't really know.
If you look at England, it's like we have an exponential, but they're like right now they're talking about how that a new virulent strain is more effective at infecting, unfortunately. Kennedy, welcome back. Had you last semester, right, Kennedy? Kyle McConnell, welcome.
Hello.
Tracy Gooch. I've had some Gooches in the past. You have any siblings that went here a while back?
Yeah.
Yeah, it's probably about 6 years ago I had a Gooch. You have an older sibling that old?
Yeah.
And Cosmo Rodriguez.
Oh.
Cosmo. All right, so this is pretty good shakeup. Oof. I'm glad that you all made it, actually, that everybody made it today. That's awesome. Good. Okay, without further ado, let's take a look at the week. So each week, those of you that were here, not a lot has changed. Each week, you'll be able to go right onto the page where it says current. This is a document you want to download. You want to change that document name to something like your name gases or something like that so that it doesn't get lost. If you want to print it out, you're more than welcome to. I love having printed copies, mainly because I'm writing with a camera and it's easier for me to do it in that fashion. But you basically click on that and boom, it's right here. You download it and then you go here and you either save it to your Google Drive or whatever. And that has all the notes and work. And it's all in one beautiful place. So if you print it out, it is a very sweet thing because then you can punch some holes in it, put it in some type of ring binder. At the end of the semester, you'll have all of that ready to look at. So that's very nice. Here are, every time you log in or whatever, you'll go to the best tutorials that I've seen if you want. If you're having trouble with the topic, this is Tyler DeWitt's page. We have covered a lot of this, it's in alphabetical order. You can see gases. He's got so many things here. You may not have to watch them all, but if you're having trouble with kinetic molecular theory, you can click right on that and it will take you right to him. And you can watch him. It's like the Backstreet Boy of chemistry or whatever, you know. So if you take a look, pretty good. Each of these, they're not usually too long.
This is the first lesson already.
About 10 minutes. Some of them go a little bit longer, but he does a really nice job. He's got a higher budget than I do. So you'll see, you know, he uses these whiteboard things and stuff like that. So I can't suggest that enough if you're having trouble. Today we want to discuss pressure and units, and then we want to do lesson 10A, pressure manometers. But we're only going to do the pressure. Today is going to be a very easy day for you. So basically, you would click onto that right there, and you can read these notes. We can read them together. Basically, pressure is gases pushing and expanding. It's in their nature. You know this. If you've got a balloon at home or whatever, you might want to have it out while we talk about this so that you can make a gas and collect it in a volume. Gases will take the shape of their container. So if I blow this up, there's the shape. Now, right now, currently, this balloon, let me go ahead and switch to, so you guys can see the big screen. So you can click on me and just mainly see me, right? I think that's how this works, hopefully. You can find some way to just see me. But if we look at this balloon, there's pressure out here pushing on this balloon, and there's pressure inside the balloon pushing on, you know, the outside, pushing away. Those pressures are, all the forces involved are currently equal. Otherwise, the balloon would be getting bigger, or getting smaller. We can fill this up a little more. So I've increased the amount of particles in there. So that means that there are more particles able to collide with the edges of this balloon. But again, the pressure is now equalized after so much time. The volume went up. The balloon got bigger because I put more particles in there. So we have pressure, volume, and particles. Now, let me pose this question. What if I were to have a source heat this balloon like a hairdryer or something like that? What do you think would happen to the particles inside? What would they start to do if we heat up those particles? You've ever seen like a, you know, a cartoon or whatever, and you've seen like somebody like sitting down and then somebody puts, you know, a little bit of heat under them. What do they normally do? Or if you touch a hot pan that's laying on a stove, you touch it. What do you do when you touch it? You guys are shy. If you touch a hot pan on a stove, this is not it's not about pressure or anything. You touch something hot, what are you going to do with your finger that's touching it? I'm just nervous about you guys now. I'm worried that you guys don't know how to respond if you touch something hot.
I mean, you get burned, so you pull it away. You pull your finger away.
You pull it away. Good, Brianna. You move it. You move it. Oh, we got a direct message. I didn't read it though, but somebody sent me one. Burn it and pull it away. There we go. Yeah, there we go. So you pull it away. You move it. And that's the key. If we start heating these particles up, they start moving. They start moving faster. As they move faster and faster, they're going to hit the edges of this wall more and more. That's going to cause it to spread out more. Or let's say that it can't spread out more. Let's say I'm sitting here holding it as tight as I can, and it's trying to spread out more and more and more. The pressure in this balloon is going to be going up. If that pressure gets too high, that's going to cause this balloon to pop, right? We know if the balloon gets a hole in it, all the pressure inside goes to the outside because of the elasticity of the balloon. Good, good. So you can easily see pressure by a gas in a balloon. The reason it stays around is because the gas inside is under pressure, pushing on the walls in every direction. If you try to squeeze that, you can feel the gas pressure increasing, pushing against you. Try it once. I don't know how common it is for you guys to have balloons at home. If we try to squeeze on that, we can feel that pressure pushing back. We can feel it pushing back, right? How many of you have ever tried to blow up one of these balloons? Anybody? This is one of those big old long balloons. You've never tried to blow up one of these? Have you tried one? Somebody? I have. Maddie, how were you successful?
No, it was very hard.
Right? What happens whenever you try to blow it up? You get that right here.
I almost passed out, so.
Stand up and do it. You could pass out. Let's see if I can do it. Oh, wow. Look at that. I got a little bit. Let's try again. It's so hard. But if we take a look, the gas in here is still taking the shape of this container. It's a long cylindrical container. That might be as much as I can get this. If you've ever seen a clown do this, usually they have like a little pump thing, right? Yeah, the pressure inside and outside. This is so the elasticity of this balloon is too much for my lungs at this time. I could stretch it out and take my time with it a little bit more, but it's too high. Let me see if I can get it back up to there. There we go. So what I'm going to do is I'm going to tie this. We've already said that gases take the shape of their container, right? So if we take a look, we take and we shift this around. You guys have all seen this type of thing before, where the person makes basically a little dog, right? Anybody afraid of balloons and the fact that they can pop? No? Been a while since I made a puppy. Let's see how we did. Not too bad. Like a little wiener dog or whatnot. But again, gases take the shape of their container. Now, if I pop that, that gas will go throughout the entire room because they also take the volume of their container. All right. So what you're going to do for the rest of the day is, if you'll take a look here, let me share this with you. I'm going to take you through a lot of different demonstrations with gases. So remember, this is lesson 10A on the calendar. You're going to want to watch this pressure defined video, and then converting pressure. Now, tomorrow, stop there, because tomorrow we're going to watch atmospheric pressure, and then we're going to talk about manometers. So today, not too much, but we're going to define pressure and what it is. You'll want to watch this video. It's not, let me see if I can, it's only 7 minutes. And then I'm going to go through this video that's 5 minutes right now in class. But if you have trouble, you can always go back and watch this video. So hopefully at this point, you've had a chance to download or print out the notes section. Let's take a look at this together. So this is how a lot of things are done in this class, unfortunately. Even when we're here, basically this is projected up on the projector and behind me. And we go through it. So this packet has everything that you need to discuss gases. Here are the objectives we want. Here's the definition of pressure, which the video is going to show. And the device that measures pressure is known as a barometer. You may have a barometer at your house. Basically, it's a device that measures the pressure in the air. Sometimes you have like a basic, if you've ever seen it, like a pressure gauge that the nurse puts on you or whatever, there's that line of mercury that goes up and up and up. That's like a barometer. There are all these measurements for pressure. This is the one we use in the United States, PSI. Does anybody know what PSI stands for? If you got a car or you got a bicycle, you see PSI on the tire. Anybody know what that stands for? No mechanics in the house. Well, if pressure is force per area, PSI must stand for a force. Does anybody know what force would be that starts with a P in America? America. How many force units do you put on the earth? How do you measure that? How much force you put on the earth? You don't have to tell me how many forces you're putting on the earth right now, but what's the unit we measure that on? Here I am standing on the earth. And I get on a thing that tells me how much force I'm going to put on the earth. What is the unit for that? I got to get better at using the chat. You guys are probably all typing into the chat, but I'm not looking. Nope. You're not typing into the chat. When you go to the doctor's office and they measure how much force you put on the earth, what do they measure it in?
It's pound.
You got it. It's pounds. The class gets long if nobody's willing to talk up. It's pounds, baby. It's pounds. You want to know how many pounds are in for every unit area? Can anybody think of an SI for unit area, what that might be? This is a little bit harder. Well, we measure area in America just like they measure it in other places. You have a length and a width. So this is pounds per square inch. PSI. Right now, all over every square inch of your body, you're feeling 14.7 pounds pushing on you. It's been pushing on you all your life, so it doesn't feel like much. But if somebody were to take their finger and go, bah, with 14.7 pounds right there, oh yeah, you'd feel it. But currently, that's all around your body right now. Kilopascals is one we don't use much in here. Torr in mercury, millimeters of mercury, they're the exact same. The one we use a lot in here is 1 atmosphere. 1 atmosphere basically just means the pressure of that whole thing that we call all that gas above us, that atmosphere pushing down on us. It's one of those. So 1 atmosphere is equal to 760 millimeters of mercury, is equal to 760 torricellis. It's just called Torrs, but it's named after Torricelli, is equal to 14.7 pounds per square inch. So the best math that we know in here is dimensional analysis. So if it says convert the following to atmospheres, and it starts us with 744 millimeters of mercury, the way we do this is we set it up. Whatever's up here has to go on bottom of the next step. We want to go from millimeters of mercury all the way to atmospheres. So we need the number for millimeters of mercury, and that is 760 millimeters of mercury. And we know by looking up here that 760 millimeters of mercury is equal to 1 atmosphere. Since we want atmospheres, atmospheres has to go on top. When we look at these two things, we know that millimeters of mercury will both cancel out. And then we can simply put our calculator, we can put the 744. And since the 760 millimeters of mercury is on bottom, we're going to divide by 760. and boom. We get 0.9789 atmospheres. Now I know that you're asking, well, how many significant digits is this going to have? Well, it's not based on these numbers up here because these are considered exact numbers. So these all have unlimited significant digits. These do not, even though it's 1 atmosphere, it's 1.0 to infinity. It's perfect. These do not determine the sig figs. How do we get the sig figs? It's whatever we start with. All of those are non-zero digits, so all of these are significant. There are 3 significant digits there, so we will need 3 in our final answer. Now, if your calculator's in scientific notation, it's going to look a little different. So remember, we changed that by hitting second DRG and going to psi or going to flow. If we're in flow, that's normal. So that's going to be 0.97, since this is 8, followed by a 9, it's going to go up to 0.979 atmospheres. Boom. Let's check this one out. This is 1.40 atmospheres to millimeters of mercury. So again, we go up here, we find our help me out, our equivalents. So we know that atmospheres goes on bottom because we want it to cancel out. Every 1 atmosphere is 760 millimeters of mercury. So atmospheres cancel out. 140 times 760, I'm sorry, 1.40 times 760. We get 1,064. This only has 3 significant digits. This 0 right here is to the right of the decimal and terminating, so it is significant. So we get 1,064, but we can only have 1, 2, 3 significant digits. So the 1, 0, and 6 are going to be our significant digits. The problem is if we just write 106 millimeters of mercury, if I owed you $1,000 and I gave you $106, would you be happy? Probably not. That 4 cannot be significant, but we do have to maintain its place value. So that would be 1,060 millimeters of mercury. All right, you're to do 2, 3, 5, and 6 on your own this evening. The other thing you're going to do is this conversion of temperature. It's likely that a teacher last semester taught you how to convert from Kelvin to Celsius, but this semester it really becomes very important. So Kelvin is based on an absolute scale. 0 Kelvin is the coldest that it can possibly be. At that temperature, electrons stop floating around the protons in the nucleus. Motion completely stops at 0 Kelvin. Well, we know that at 0 degrees Celsius, water freezes. Big whoop. Water freezing is not that big a whoop. We know that at 100 degrees Celsius, water boils or starts to vaporize. 0 degrees Celsius, all motion of particles stop as it is known. Oh, good, Maddie, I just saw that. Square inch, good. All particles stop. This is negative 273 degrees Celsius. At 0 degrees Celsius, that is 273 Kelvin. And at 100 degrees Celsius, that is 373 Kelvin. So in order to go from degrees Celsius to Kelvin, you add 273. So if it's 100 0.0 degrees Celsius. That is 373 Kelvin. Notice I don't put a degree sign on there. And since this is addition subtraction, we're going to always go with the same decimal places of the ones we're given. So if it goes out 1 decimal place, we go out 1 decimal place. If it is Kelvin and we're trying to go to degrees Celsius, you take the Kelvin and you subtract 273 to get the degrees Celsius. So 345 minus 273.
The answer is 72.
That is 72 degrees Celsius. And if we take a look here, this is the ones place. So since this is addition subtraction, this also goes to the ones place. So you should do 13, 14, 15, 17 for tomorrow, as well as 2, 3, 5, and 6. And you will also want to watch those pressure demonstrations. Basically, that will give you the idea of what pressure is. So please on that, make sure that you look up pressure defined demo. Question? As I said, I would give you time to go get all of that done. You guys have 18 minutes to work through that. That way you don't have any homework for this evening. If you want to stick around and you have questions or whatever, by all means, that's what this time after is for. But this would be normally time that you would work in class and I would go around and help. So if you find that you have a problem after you get off, by all means, come back on and the Zoom will be open. Otherwise, have a great day, guys, and we'll see you tomorrow to talk about manometers. Bye.
What was the assignment again? My bad.
No worries. So if anytime that you have an issue, like when you want to find out what the assignment is, the easiest way to do that is to come to the current work right here. And then it will tell you lesson 10A, pressures and manometers. And then basically you're going down through here and you're watching this video and you're working through these problems. So that's it. Just
Great, thank you.
package. So this is unit 9. So page 1. Ooh. Still feel that.